What is bounding box regression? It is basically when you train a model to predict the coordinates and the size of a bounding box surrounding the object. It's used in tasks such as detection, localization, tracking, and so on, right? When you're doing that, you need a metric to judge how good your model is, right? Normally, people use IOU as the metric, which is just the intersection of A and B divided by the union of A and B. So you can see something like this would have a low IOU. This is a high IOU. This is just one because A intersection B equals A union B here, right? The reason why they do that is because it has got two very good properties. It's scale invariant, that is, it does not vary as you vary the scale of the object, and it captures nice shape properties, right? But what happens normally is that when people train the model, instead of using IOU, they use L2 and N1 norms to train the model, right? While IOU is still used as a metric to judge how good the model is performing, right? Inherently, the model just learns to minimize an L2 and N1 norm and not essentially maximize IOU, right? And that is what the authors of the paper realized. They realized that there's perhaps not a strong correlation between minimizing end-to-end N1 norms and maximizing the IOU, right? There are some problems with these norms, right? They are not necessarily representative IOU, they're not scale invariant, and there's like a lack of regulation between different parameters, right? To deal with this in the past, people have tried different bounding box representations, such as modeling it as a displacement in RCNN and just using log in W and H to capture scale properties, right? But in general, it's like not that efficient, right? You can see an example of this here, where let's say you have two bounding boxes, they're X, Y, and H of X. We are only varying the W. One is like a W of 5, and the other point is a W of 15, right? In this first case, the L2 norm would be 5 minus 10 squared, which is 25. Again, like it would be some constant added to this, but that's not there just for visual clarity, right? Value I would be 0.5, which is 5 by 10, right? When it's 15 and 10, the L2 norm would be the same, but your IOU would change because your IOU would be 10 by 15, which is 0.66. As such, we can see that like IOU and L2 and N1 norm is not necessarily the same. Right. So why don't people use IOU, right? Why don't you just simply define a loss as 1 minus IOU, right? Well, like doing this has some advantages in the sense that IOU is scale invariant. IOU is differentiable for 2D bounding boxes. It has got other nice properties such as non-negativity, triangle inequality, and so on. But the disadvantage is pretty big. It's that when A intersection B is 0, your IOU is 0, and then your gradient of IOU is also 0, right? So you're not backpropagating anything in that case, right? Also, like both of these things have got the same IOU, even though this is perhaps more closer to the ground truth compared to this, right? The solution that the authors of the paper came with this is to extend IOU to not be 0 in such cases, right? Thus, they propose generalized intersection over union, right? How do you calculate the generalized intersection over union? You find the smallest convex shape C, enclosing both A and B. For rectangles, this would just be a rectangle, right? And then you calculate the ratio of area between C minus A plus B, which is like this, and you divide it with the area of C, right? This represents a measure of the empty area between A and B. You subtract this ratio from IOU and you have a generalized intersection over union, and then you can define the loss on it as just 1 minus GIOU. Right now, generalized intersection over union has got nice properties. It's correlated with IOU, as you can see. This line represents like the identity line. Obviously, when IOU is 0, GIU still varies. But like as IOU reaches 1 GIU and IOU converge to the same position, they diverge a lot here, which makes sense because it's like the case with the separating, right? Uh, and in general, it has also got all of those nice properties, which makes IOU desirable, right? Like it's scale invariant, it's non-negative, triangle inequality, so on and so forth, right? But like, how do you calculate GIOU? This is like the algorithm here, but like to put it in short, you can like find these 4 points. Like let's say you're given these 4 points, then you can easily find out that that like the rectangle C would consist of the point here and here, and then you can just like find these dimensions, calculate the area, while the intersection would consist of the points here and here, and you can just calculate that. Using this, you can also check whether intersecting or not. That is pretty easy, right? But the idea here is that you can see that it's and as an intersection over union is kind of a polynomial in these four variables divided by a polynomial in these four variables. So it's actually differentiable in 2D bounding box cases. So you can propagate it backwards, right? So what what the authors did is that they trained it using I love GIOU versus MSI, and they saw the results on the COCO dataset and a Pascal VOC dataset, right? And in general, it relatively performs well in IOU metric and both in like when you use generalized intersection over union as a metric, which kind of suggests that yes, they are correlated in general, right? As a result, in conclusion, the main takeaway is that optimizing L2 and N1 does not always optimize IOU. IOU as a metric has a lot of advantages, and extending IOU to GOU allows us to use its advantages without its drawbacks. Thank you.